Hello, good morning.
Good morning, sir.
Good morning, sir.
I don't know what is going on. Should we still wait or we can start?
So let's start. They will come. I'm putting it on the platform.
Okay.
So let's start.
Okay, so I was just going through the slides. I prepared whether everything is in there. Good morning once again. So, from last week, we've been dealing with light. We started with waves. We ended up with light matter interaction. We looked at some of the interactions. And today, one particular property of light that we call the diffraction. That is what we have to look at. In fact, today I have a lot of questions in the slides, but we may not go through it. I'll leave it for you. I'm trying as much as possible that I can close earlier than the normal time. Maybe if I can use the 2 hours to do the class, because the slides are not plenty. Then the next 2 hours, you will sit down, then go through, then solve the questions. If there is a need for me to come on board later, we can just discuss an hour or 2 hours meeting apart from today's one. Then I'll cover up for what you want to understand. Is that okay? So that is what you have to be doing today. So
Okay.
the first thing that we have to do is look at the principle of diffraction, look at one optical component called the diffraction grating, and inside the grating too, we can use only a single slit. We will have to look at what a single slit, how you can use it. Then look at something we call the resolution. And under resolution, we have something called the resolving powers. You have to look at that one too. Then there are two particular scientists that actually influenced diffraction a lot. We call one Fraunhofer and Fresnel. So we look at them and what they spoke about under diffraction. So fast forward, let's go on. So if you remember, under interference, you said that light has to pass through a hole. And when I was even illustrating this, I said when you are teaching your students rectilinear propagation of light, you do this experiment where you you punch some holes on the cardboard, then you put the light at one side, then the cardboard you can use about three, then the observer or the student with the eye is at the other end. Then you start moving it and you tell the student to observe what is going on and also explain what is going on. Is that okay? That was actually explaining how light travel in streets path. Is that okay? The same slate that you created, that is the same slate we are looking at here. But this time around, the slate we are talking about here is very, very, very small. Is that okay? A small to milli, small to say even a micro, like very, very small. You see, your hole was big enough that maybe your finger can even pass through. Is that okay? But interestingly, anytime so that one is called a slit. So you see a hole like this here. Let me use a laser pointer. You see a hole like this here, we call it a slit. Is that okay? Light is going to pass through. But interestingly, you see when light passes through a hole like this, ideally we may think that as it was before entering, it should be like that. Is that okay? But interestingly, it doesn't happen that way. It doesn't go as this pattern as it entered before. It moves in this particular manner, like a spherical way of movement, and it diffuses to a different places. Is that okay? And this is what we call the diffraction. So diffraction is particularly when light encounter a small hole or aperture, and at the end of the day, it's spreading away. Is that okay? So this is diffraction. So light doesn't enter a hole and this happens. Light enters a hole, but this is what happens. Is that okay? Now, this is what you're calling a diffraction. So you see, this is spreading out of light from its initial line of travel. Is that okay? So this is the initial line of travel. Is going straight in this manner. It exits at this end. Then you see there's a spread out. It goes to where it wants to go. And diffraction will occur when one light actually passes through an opening, exactly, around an obstacle. When you see an obstacle, anything that is a hindrance, so you have a small opening to enter, exactly, or any sharp edges, exactly. So diffraction may happen. So we should be expecting that anytime we pass light through a particular hole, either big or small, we should expect something we call what? A diffraction. Now, if you remember again, when we were dealing with Thomas Young and interference, we used a diagram like this. Let me zoom in. Okay. We used a diagram like this. And the first diagram, we said that the light will pass through, then we will get it diffracted. Then we will be having another slit here. That is slit 1 and slit 2. Is that okay? So this time around, another diffraction happens and we get our constructive and destructive interference. The same as what we are discussing. So it means that in Thomas Young, diffraction has to happen before what? Even the interference has to happen. Because right after the light passes through, the first opening of the slit, diffraction do happen. Is that okay? And you see that this time around, the pattern that it's used to enter the hole is not the same pattern it is exiting from the hole. You see this time around, it's a spherical way, meaning it's spreading out. Is that okay? After entering the hole. Okay. Now, When diffraction do happen, we should be expecting something like the Hinge principle happening, where he spoke about the fact that if we have a first wavefront, it generates a secondary wavefront, it generates another secondary wavefront, it generates another secondary wavefront. But interestingly, something we call a constructive and destructive doesn't happen only in interference. Under diffraction too, it do happens. And I'll show you why. Is that okay? So under diffraction, we will still get something called the constructive, and we still get something called the what? The destructive. Now, someone may ask, so what is the difference between interference and what is the difference between interference and diffraction? In fact, one way or the other, they are all the same. Their differences is very small. And someone can, of course, explain it when we are using the slate, because under interference, it purposely needs two slates before it can happen. Is that okay? But under diffraction, only a single point or an obstacle can cause a diffraction to happen. Is that okay? And even if we are getting a constructive and destructive under interference and diffraction, they are still two different things on its own. Is that okay? And under diffraction, we should be expecting that the number of ways that is exiting is very huge. Is that okay? So the light enters and a lot of waves is going on. Under interference, we have a particular number of waves, because one wave have to meet another wave to form a crest and a trough to get our constructive. Another wave have to meet another one to either form a crest and a trough, meeting to form a destructive. Is that okay? So here, the number of waves that is being superimposed is very few, and the number of waves being used under diffraction is quite huge. Is that okay? So it is important we know these two differences. Now I'm going on. Now, a very typical example. You can see that in our everyday life, even when you are standing in the sun and you check your shadow very, very well, you may not get the edges of your shadow as sharp as it is. There may be some faint and blurry or fuzziness around the end here. Is that okay? And it's very, very normal. Even in imaging, even in optics, no matter how accurate your lens are, when you're using it for imaging, you may not get the sharp edges that you want. Is that okay? Unless it's being pre-processed in mathematical ways, like computational ways. But the optical system itself will not give you that fine image. Is that okay? And this is because of what? Diffraction. Is that okay? Because at the end of the day, the light that is passing through that small aperture do spread. Is that okay? So the spreading actually gives these edges not to be sharp. Is that okay? So it is very, very important. Diffraction is a problem in optics, but we also use it in solving another ways, one way or the other of a problem. Is that okay? Now let's do a very small recap under interference, and particularly Thomas Young, the experiment that he did. And if you remember, I told you that anytime we have, let's look at the first diagram here, chart here. Anytime we have a point source here, and we have two openings, our slits here, and of course, the distance between slit 1 and slit 2 is D, we can find something we call the path difference. Is that okay? And here is the first ray from the first slit, that is R1, the second ray from the second slit, that is R2, and we are interested in the path difference of R1 and R2. And if you remember, we just used sine to do this. And we said that if you want to find a small path difference here, it means that the path difference is going to be d sine of theta, which makes sense. Is that okay? Because the angle here is opposite, and here is going to be our what? Our hypotenuse. So we are going to get d sine what? Theta. Now, from this equation, we were able to derive how the path difference is supposed to vary, or the wavelength, so that we get something like a constructive and something like a destructive interference. Is that okay? And we were able to find out that if we have two waves that are in phase, it means their wavelength of course, it's just going to be one. Is that okay? But if we have two waves that are not in phase, meaning they are out of phase of 180 degrees, we should be expecting about the wavelength divided by 2. Is that okay? And if that is the case, we derived our phase difference to be equated to a particular wavelength with a what? With an integer. Is that okay? So we said that anytime we have 2 lambda or 1 lambda or 3 lambda or 0 lambda, multiplying the lambda, that is our wavelength. It's possible that you can compare it to what? Path difference and the angle and the distance between the what? The two slits. Likewise, because they are out of phase, and I think someone even asked the question, why this particular fraction here? Is that okay? And it's because what? They are out of phase. So if they are out of phase, we expect the wavelength what? To shift. Is that okay? And if we do that, we bring the integer here, it can cover up the 180 out of phase issue. And you know, anytime we are dealing with, say, diffraction, interference can also play a role here. So I just brought this one here for you to appreciate what I'm coming to do next. Is that okay? Please, can I go on? You can give me a thumbs up, maybe. Great. So now let's go on to diffraction itself. Now with the diffraction, we don't need 2 slit openings. We need only 1 slit opening. Is that okay? And under the 1 slit openings, still the waves coming out, some may superimpose each other, and still constructive and destructive interference may occur. And here too, it's possible to derive something we call the path difference. Is that okay? Now let's imagine something. If we are considering half of the slit, now the slit starts from this end. I don't know if you can see my laser pointer, where the ray 5 is exiting out. And another point ending is this one, where ray 1 is exiting out. So we have ray 1 and we have ray 5. Is that okay? Now I'm dividing this into 2. So the very middle ray is going to be ray what? 3. Is that okay? So I've divided it into 2. And the distance between the opening, is that okay? That's the width of it, is what? Is A. So if I divide it by 2, it means I'm going to get 2A at the top, and sorry, A over 2 at the top and A over 2 at the down. Is that okay? So half of the A, half of the A. Now let's look at something. I am interested in the wave phase difference. So here, the phase difference I'm going to talk about is between the ray 1 and ray 3 for the down aperture. Is that okay? And for the top one, it's going to be ray 3 and ray 5. I'm going on. Or I should repeat again.
Please repeat what you said again.
Okay. So let's go back a little. When you look at this chart, this is from Thomas Young, and he said that if we have 2 openings, that is a slit 1 and slit 2, they have 2 apertures, and the distance between the 2 of them is D. And for the first slit, the first ray that exits is R1, and the second slit, the second ray that exits is R2. Is that okay? I can find the phase difference between the R1 and R2. Is that okay? And that is the small distance that we are talking about here. Is that okay? Because ideally, R2 is way longer than R1. I want to know the difference between the R1 and the R2. And that is this distance. Is that okay? And we derive this using just a normal trick, because you can remove this end and bring it here. So the first slit here, the second slit here, the distance between the 2 slits and the angle of it is okay in the phase difference. So if you use a sign, it means that we are going to get D over the what? The phase difference. If you find the phase difference, it means you are going to get what? D sine theta. Is okay. Where the D here is the angle between the 2 slits, sorry, the distance between the 2 slits, and the phase difference is what we have down here. Is that okay? And our theta here is what we have here. And it's the same ideology that, of course, we are bringing it here. Here too, we have our big opening. Is that okay? Instead of the D at the other end, here we are using A. And here we are not using two different slit opening. In diffraction, we need only what? A single slit. Is that okay? For diffraction can occur only in a single slit. Interference occurs only with a two slit. Is that okay? Diffraction can occur in only a single slit. And even diffraction can occur in a double one too. Is that okay? It can occur in a single and a double one too. Now, with a single one like this, we are saying the distance between the two openings is okay. How where the aperture is that the hole is A is okay. And here we are dividing the hole by ourselves as 2 is okay. So that the first end here is going to be A over 2. The second end here is going to be A over 2. And now the ray that is exiting the 2 over 2 down here, we have one ray 1 here is okay. And the last one that is exiting is ray 5. In fact, it's from ray 1 to ray 5 is okay. Now, when we divide our opening or our aperture by 2, it means that the middle ray is going to what? Ray 3. Here, I am interested in finding the phase difference again. Is that okay? And if you remember from Thomas Young, the phase difference was what? D sine theta. Is that okay? Here, our theta here is going to be at this angle. So if D sine theta, here it's not D again, it's A over 2. Is that okay? So we are going to remove the D and replace it by A over 2 sine theta. That is going to be the half of the aperture. Now let's look at the upper half of the other aperture. This time around, it's still going to be the same because we are talking about from ray 3 to what? Ray 5. And we should still be expecting A over 2 sine what? Sine theta. Is that okay? Now let's go on. In fact, because if we are talking about, say, destructive interference, where we will get a minima, we have to divide 2 by what? Our wavelength, because we know that wavelength is a full cycle. Is that okay? So if we divide it by 2, it means there's going to be a shift out of phase, is that okay, by 180 degrees. Now, if we do that, we can, of course, equate it to what? Our phase difference. We know that our phase difference of 1/2 aperture is A over 2 sine theta. Now, it's going to be equated to what? The wavelength divided by 2. Is that okay? And this particular one is for a minima, that is a destructive interference. Now, if we cancel, maybe let's do that some small change of subject. What we had here before, let me write. But anyways, do we understand up to this point? This is when we divide the slit into 2 here, we find for this end and we find for this end. Give me a thumbs up so that I continue on a bit. Am I online? Okay. So now this is dividing our aperture by 2. Now, if we want to just find the sine theta, it means 2 is going to go here and A is going to go here. And at the end of the day, we should be getting our sine theta of course, by our wavelength on A. Is that okay? These 2 here cancel these 2. Is that okay? And I just brought the A up here, down here. Is that okay? And this is when we have it what? At 2 ends. That is dividing the slit into 2 equal what? Halves. Now, what if we divide the slit by 4 equal half? Is that okay? Now, dividing the slit by what? 4 equal parts. It means that this time around, we are not going to get A over 2. We are going to get our phase difference as what? A over 4. Is that okay? And now our phase difference here is going to be what? Sine, sorry, A over 4 sine theta. And comparing it to wavelength is going to be what? Wavelength divided by the 2. Is okay. Now, if we just make sine theta the subject, it means that the 4 here is going up here, the 2A here is coming down here. Is that okay? So the 4 will cancel, and at the end of the day, we will get only 2 left up there, multiplying the wavelength divided by what? A. And that is what we have here. Is that okay? So when we divide again, say we divide it by 6 equal parts, we should get an equation like this. We divide it by 8 equal parts, we should get 4 lambda divided by A sine theta. Is that okay? So the general condition for a minima to happen, that is a dark interference to happen, or say a dark fringes to happen, is going to be created as this equation, because at the end of the day, anytime we divide, we are getting only the parameter here being changed. The n here is okay. So from 1, we went to 2, we went to 3, we divide again, so we go to 4, we get to 5. So it's a general condition for a minimum to happen. Is sine theta equals what? M here, our wavelength divided by the what? The A. Please, can I go on?
Please go over it.
Oh, I don't know which part I should go, but
The latter part of it, the formula.
okay. So you see when we started dividing, when it is divided, if the aperture here is divided by only 2, we generated this formula. Now, if the aperture, that is the hole, is divided by 4, we generated this formula. And you can see that the difference between the first formula and the second formula is only, the changes is only here. Is that okay? We still have our wavelength divided by E, wavelength divided by E, but here it's only 2 that changes. Now the aperture that we are having, we divide it by 6 again. And you can see that the formula here and the formula here, they are actually the same. The only difference here is what? The integer changing from 2 to what? To 3. And in fact, when we do another one and we divide the aperture by say 8, you will see that 3 will move and 4 will come. Is that okay? Because sine theta equals 4 lambda over A. Is that okay? So we generated a general formula for the condition. Is that okay? We want to know at which end are we going to get our what? Our minima or our dark fringes. Is that okay? And that is this equation. It means that if we have this, we may know how to alter this to get a dark fringes, or the angle that you have to actually move to get a dark fringes. Is that okay? So this is a general condition formula for a what? Dark fringes to occur in diffraction.
Okay, sir.
Great. So now you can see that if we have the same formula, if we have this, we can actually define each end here. This is the dark end. Is that okay? We can actually define the dark fringes for each path. Is that okay? So the y1, the y2, the negative y1, negative y2, these are the points that we should be expecting. And here was when we divided the aperture by 2 to generate the formula. Here is when we divided the aperture by 4. Another formula can come in here when we divide the aperture by 6. Is that okay? Another formula in here can also come. Is that okay? So actual sense, we expect the fraction to occur this way. This is our maxima. This is our minima, minima, minima. Is that okay? We have another maxima here. We have another maxima here. Is that okay? But this end is where we have our total darkness. That is the dark fringes or destructive interference. Is that okay? Now, I have a question here. I told those who just joined, I said today I will finish up very early. Maybe if I'm even lucky, I can use like 2 hours to finish up. What is left is not plenty, but you will not solve any question. When I finish, you use the rest of the time to go through the questions yourself. And if you want to discuss with your colleagues and call the person, that is fine with me. Is that okay? But we will not go through any question. Then, if you are done with everything and within the week, you still need some guidance with the questions and everything, we can just reach out. Then we schedule, say, an hour or an hour, 30 minutes to finish with the questions. Is that okay? So there are a lot of questions that I've placed in here. Just try and go through. Some is from the model, some is from other books that I have compiled. So
Serabi,
let's go. Yes, madam.
uh, I'm not trying to compare you, but some of the other courses, the
Mm,
teachers give them some tutorial questions whereby they set the question, they take the question right from the tutorial questions. I
mm,
think to make something easier for them due to the time schedule and the stress involved. So
mm,
it's only our side that we don't get that opportunity. So
mm.
do you find that the thing is so tight. Are you people going to help us in that way, giving us tutorial questions and then guiding us to learn?
Sincerely, this is not my decision. Maybe it will be the coordinator's decision to take whether to give a tutorial question and he will set the exams from the tutorial questions and all. What uh, I'm told to do is to be giving you questions, a lot of questions, because you are asking of questions. So
Okay,
one way or the other, these are my tutorial questions. Is that
okay,
okay?
okay,
And because I'm not in charge of setting the questions, I can't reassure you that the
okay,
questions here is from me. My work is for you to understand what is going on. Is that okay?
okay.
So I think if in case of anything, maybe you can
Water
just
brand.
channel the conversation to the coordinator, which it will be he will be the very right person to answer this. Is that okay?
Okay,
Mm-hmm.
sure.
Mm-hmm.
Thank you.
You're welcome.
Hello,
So
sir.
now let's go on. So yes,
Good morning. Sir, please, the
good
questions that
morning.
you're talking about, I just joined, so I would wanted to know where is it posted? Or is it going to be given after the lesson?
Oh, I'll share the slides.
Okay.
So if you do you understand?
You mean it's on the slide?
Pardon?
So
Please. Mhm.
which questions are you talking about?
You know, you just said that you are going to give us some questions that we have to go through
Oh
as
no,
we.
that is the questions from the slides. These questions.
Oh, okay.
There's no other special questions that I've written. So as I'm preparing the slides, I just chip in questions. And you know
Oh,
that you've been doing some during the class. But this
yeah.
time around, I'm saying we will not put some time on to set the questions because I want to try and finish early. Is that
Oh, okay,
okay?
okay,
So
okay.
I'll keep the questions for you. When I close them, you solve it yourself. Is that
Oh,
okay?
okay. That's fine. Yes, sir.
Mm. Yes, Ibrahim. Hello. Okay. Maybe it's a mistake.
Hello, Serabi.
Yes, sir. Okay, come on board.
Please, I hope you are fine.
I'm doing this and
Hello.
yourself. Yes, sir. I'm
Alhamdulillah.
listening, sir.
Sir, please, we are on our knees. I'm just want to ask something small to what our sister Felicia said. Say, not
Your line
like
is actually breaking. If you
we are
readjust your
comparing
position.
our course to other courses, but we are on the same platform. It's okay now. Hello.
Yes, sir. I'm listening.
I
I'm
mean, I'm
managing.
saying that. I
Yes,
just
I'm listening,
want
sir.
I just wanted to do some
Mm,
addition to what my sister Felicia just said. So it's not like we are comparing physics course to
mm,
uh, other areas, but we are on the same platform. We are on the platform with those who are doing, who are majoring in biology, who are majoring in chemistry. Say, always you will see them, their coordinators sharing something with them, of which is very, helpful one way or the other. But in our case, sir, it's not like that. Looking at the book that we are learning, the model very voluminous, very comprehensive. You don't even know where to start and where to end. It, the same thing happened. That was last semester, block 1 or block 2. There is the electronics. Say, by the time you realize, if not past question that we had somewhere, by now we would have all been a failure. So we are pleading. We are pleading on our behalf. Kindly talk to the coordinator. Once he has given you the opportunity to be in charge of what of the lectures, then hopefully when you speak on our behalf, maybe he will, one way or the other, one way or the other will listen to our cry, because we are not. The course is something else. 4 weeks for the books. We have family. We have where to go. Then the exams will be something else. Please, kindly do something about it, and we will be grateful. Please.
Okay, Sir George Sans is up here, Sir George.
Sir, good morning, sir.
Yes, good morning.
Okay, sir, please. We beg. Yesterday, because of what we are discussing here, we formed a WhatsApp group with the thermal physics. I'm saying it because we are all physics students here. So when I talked to Sir Yusuf, he said that I should form a WhatsApp group. Then I should add him. Then you also try and add Dr. Peter, so that on the page, if we have certain things that we want to say, we can say. Then Dr. Peter will hear, then he will also make input. Because one thing I've realized is that for some of them, after that I've witnessed it, say Festus, and they try and then get the areas, especially for the quiz. For us, they have done it. When we are doing electricity and magnetism, they told us that doctor said we should learn unit 1 and 2 for the quiz, and it happened. When we wrote the quiz, we saw that it was the same thing. It didn't change. So we are also pleading, if you can. So far, I'm not comparing, but you are the only one who maybe you don't maybe inquire that one of the lecturer, or you ask and he doesn't give. But we have seen that whenever he's done with us, today by close of day, he has promised us that we will hear from him, from the doctor, through him, from the doctor. Then he will tell us the areas we should learn for at least the quiz. So I beg, if you can also do that for us, I will beg. As for you see, sometimes you go and learn everything, then you go and see that the questions are only coming from unit 1 and 2. Meanwhile, you have a lot of things to learn. So at least when you are safe with that headache, you prepare for the quiz. Then maybe the exams, you go and fight for yourself. Then secondly, so I beg, if you can't help us with the tutorial question, I beg you. I don't think past question is past question is past question. If we were on campus, if we stay at Cape Coast, we will get it. It's because we are far away. So I don't know why past questions is something like treasure here, that getting it is very difficult. I beg, say, try for us. If you can't get us the tutorial question, past questions, I don't think, if any letter will say that I don't give out my past questions. I don't think so. It is past question. And students are supposed to serve as a guide for learning. So I beg, if you can't get us the tutorial, kindly get us the past question. We beg. These are my two submissions. Thank you.
Mr. George, for the first call, they didn't do optics, optical, physical optics. They didn't do for the first cohort, plus thermal physics. I'm talking about the first cohort. For them, I don't think
they didn't do it.
Yes. Yeah, they didn't do thermal physics and what we are doing this morning.
Are you sure?
Yes.
Okay.
Then we are dead.
We are dead.
Okay, boss. If that is the case, you will look for a way out.
So any other submission?
But at least, say for the quiz, I beg. Sometimes I'm not challenging, but sometimes you go to the quiz, you realize that they are coming from only one session, and you have learned everything. That is what I'm saying. So it means that they set it based on sessions, but we don't know. Because I remember when I was doing the degree, first quiz is unit is half of the book, then the second quiz is the other half. That is what happened. And I think they are doing it just that we don't know. Because when you go and sit down, you see that most of the questions are coming from one particular area.
Anyways, any other submission so that we continue? Then maybe I give my final remarks to continue. Any other submission?
So Rabi, actually, it's not any different submission.
The same submission.
Except,
you are saying something?
yes, I'm saying it's not any different submission, except that you see, when we are requesting things like this, it creates the impression that maybe we are not learning, we are lazy. But then, say the truth of the matter is, to put it into perspective, the duration is just 1 month, and the things are many. We are trying so hard, but it's not easy. And looking at something like atomics, for example, it's over 300 pages. Then you bring in optics, thermal, there are many. And so it's not like we are lazy or we are trying to find maybe an easier approach. But then we want to, and easy in a way, even to even also make the course still, or let me say the program still attractive to the subsequent years. When they are talking to us and maybe the feedbacks are not good in terms of our result and things, I don't think they'll be attracted. We just want to do well, because after this also we are going to, how do I call it? We are going to impart the knowledge as well. So we just want to be able to put things into a good perspective for us in terms of result and in terms of acquisition of the knowledge. But then when we are saying that, I mean, these things and the feedback is as though like we are trying to be lazy, but that's not the impression. I just want to say that please help us in that regard. Like my colleagues are saying, we just want to pass and pass well. And it's because of the time frame and how voluminous the contents are. That is why we want it like that, please.
It's very understandable. So talking now, I don't know which one to start with, but with respect to the time frame, it's very understandable with respect to how plenty the courses are and the time you used to have to cover up, and particularly even how you should be told what to learn for the quiz. That one, there are no two ways about it, because I teach the normal regular stream, and they know that when they're going to write their first quiz, it's units, half of the units are coming. So supposing your module is about 4 units, it means the first unit is for the first quiz. And even now, they don't write second quiz, they do presentation. Then we score them for that, and they just go and write their exams. Which the exams will comprise of all the units so far. So yes, it's very understandable, and I think the course tutors too have to do that. But this time around, everything is being moderated by one person at the top, and he just assigned us to teach. So I will just tell him your price that you need to be informed about where to learn when it comes to the quizzes, and particularly because he told me to be bringing in questions in here, because one person called him that you need questions and it helps. Is that okay? So I've been trying to put questions in the slides a lot, because we can't do a tutorial set as questions with one lecture and do another one with tutoring with another period, which is going to be very time consuming. So you don't worry, I'll just tell Dr. Charles about it. He's my coordinator for this particular course. So I'll tell Dr. Charles about it, that at least you should be pre-informed about where to learn for the first quiz, where to learn for the second quiz, and if there's a need that you should have a separate tutorial set, that this is our tutorial set and this is where you should be expecting questions from. I'll just tell him about it, so that at least if there's a need for us to also meet again to discuss it, I'll bring him on board, then we all discuss it peacefully. Is that okay? I think that is what I can do for now. Is that okay? Yes, Sir George.
Sir, so we beg. Then when should we wait for the response? Because since the first semester, whenever we talk of this thing, you always tell us that you get back to us, but nothing happens, and then we go around there. So I
Hopefully
beg you.
tomorrow, yeah, hopefully tomorrow I
So I
will
beg you this time. Tell us that by Wednesday we'll hear
yeah,
from you, so that we know that.
hopefully tomorrow I'll meet him. Depending on his feedback that he gives me, I'll just let him, whether on the page he will come and give his submissions, or from what he's saying, he wants me to come and tell you, I'll do that. Is that okay? So depending on his feedback, today is Sunday, so tomorrow he will definitely come to the office. Then I'll tell him because of this and this and this. You guys need this. So
Thank you.
welcome. So so for you will not speak and you are giving compliment to everything that is going on. Okay, so Abek, can we go on now?
Yes, please.
Okay, great. So now one particular applications for diffraction under the principle of diffraction is what we call the diffraction grating. And you see, in our basic knowledge in optics, when you say dispersed light, the only thing that comes into mind is a prism. Is that okay? But one interesting thing that can also disperse a light is the grating. Is that okay? And the grating works in a very wonderful and, in quotes, a magical way. The engineering behind grating is very phenomenal. And in fact, we have a particular two types. We have one we call the transmission, and we have one we call the reflection. Is that okay? And one particular, or the engineering behind the grating, is we have something we call the groove. Is that okay? And we have something we call a distance, a D. Is that okay? That's separates it. So the groove is just the spacing behind, or let's say beside every slit. Now, I told you that the slit is a small opening. This time around, the grating has an opening of a length like this. So this whole length is an opening. Is that okay? But the opening is very, very small, and the spacing behind that each opening is also very small. So we have one vertical opening, another vertical opening beside it, another vertical opening beside it. Is that okay? It's not one broad opening, but small openings beside it. Is that okay? And of course, we can have about thousands of these openings on a particular slit. And the slit too is not big. An actual image of the slit is something like this. And I think the last time I showed you how a slit looks like. And here we call it a groove. Is that okay? So I define an optical diffraction grating as an optical device that is made up of number of spaced parallel slits. And that is what you call the grooves. Is that okay? And I don't know, maybe I'll show you something when we go on. Now, this is how the slit tool works. So you see, the grating has small openings that we just spoke about. Is that okay? And one way or the other, through the diffraction grating, we can observe a constructive interference, a bright fringes. Is that okay? The other one, I showed you how we observe the minima, the dark fringes. We can also observe a bright fringes, which has a formula as this. Is that okay? Interestingly, if we do this experiment, we have to see this bright light and the dark light and other things. And I don't know if those who came to UCC, did you do any experiment like this where we have a light source and you use your eyes to look through a telescope and there was a grating sitting at the middle here? Did you do anything like this? Madam Fisher, you are UCC.
We did it on the optics room.
Very good. So this is a very practical example where students observe what the optical, the bright fringes and the dark fringes. And I don't know if you remember, we placed a grating here, that straight board like this. Let me show you something like this. This is the
Yes.
grating. We placed it on the stage here, and we
Yes.
were using our eye to observe a light. Is that okay?
Yes.
A straight light there. Is that okay? So anytime we see light, it means that there's something like a maximum that's happening. Anytime you don't see a light, there's something we call the minimum. That is the dark fringes that is happening. Anytime you see another light, we say there's a maximum that is happening. Is that okay? So this is a very practical example for students to appreciate how diffraction grating also works. In fact, this kind of grating that we are talking about here is a transmission grating. I told you that the diffraction grating we have two types. We have the reflection and we have the transmission. Is that okay? Transmission is it passes through to the other end. Reflection is the grating has to work when the light hits on it and it bounces back. Is that okay? So something like this, a very practical example of the reflection under the diffraction grating looks like this, where our incident, like the white light, has to hit on the surface here, and our dispersed light will go to this end. Is that okay? So here we can measure both the incident angle and we can measure both the reflected angle. So if you saw the formula I showed you earlier, we were having only one sine theta here for the transmission grating. But for the reflection grating, sine theta here. But for the reflection grating, we have to consider the two angles. Is that okay? That is sine theta I plus sine theta R. Is that okay? And this is very, very important. Is that okay? So you just have to put in mind that when you are dealing with transition, these two angles is not important. We use only one sine theta, as the formula is showing us here. Is that okay? But when you're talking about the reflection, we are interested in two angles. The angle where the angle that is incident to the surface and angle that is reflected from the surface. Is that okay? I don't know if I can go on. So there's another bunch of questions here. And now let's look at something here. We have something called the efficiency of a grating. So efficiency is just talking about how much the incident light power is actually being sent on the diffraction grating. And instead, we are not interested in the one that is going to get wasted. So the one that is incident on it, are we still getting the one that is coming out of it? Is that okay? So anytime we are actually measuring the efficiency, we are actually interested in one. The incident light, that is what? Diffracted. Is that okay? And the one that has a reference. So what we do is, if our grating is here, and say this is a transmission one, light hit on it, I'm saying that the transitioning light has to pass through. So it's diffract, then say we get our light here. Is that okay? So this is the light that you will measure for the first up here. The second down here is you will just take a standard surface or any surface, then we incident the light on the surface. Is that okay? Then you will just measure the reflectance from that surface. Is that okay? And what is here, the measurement, the value that you get here is going to be our denominator here. That is why we call it the specular reflectance from any surface. Is that okay? So here we have a particular standard surface we use. We incident light on it and we get the results from it. And we bring our diffraction grating and let the light go through. Supposing it's a transmission one, of course we do that. Supposing it's a reflected one, that one too, we let the light hit on it, then we measure the reflectance of it, and that's all. Exactly. So measuring the efficiency is quite easy. We can also bring in something that also affects the efficiency a lot, and we call it the blaze angle. In fact, we have something called the blaze angle, we have something called the blaze wavelength, and other things. And you see, in diffraction, I said we have one that is transmission, we have one that is reflectance. The reflectance, if this is the surface of the grating, the light is going to hit on the surface and it's going to bounce back. Is okay. Then we get our diffracted light. Now, how the surface is designed is very engineered in a very typical way. And you see the surface here tilts at a particular angle. You will not use your eye to see, very, very small, because it's very, very important to the wavelength that is refracting out. Is that okay? So if we have, and I mentioned that if we have something like a blaze, we can just define a blaze as what? The tilting of the groove. Is that okay? So here you can see how it is tilted here. And it's tilted in a very engineered way so that it can refract a particular wavelength out. Is that okay? So you will not see it tilted to say 90 or 80 randomly. It's tilted depending on the wavelength. Is that okay? So every wavelength has an angle that it has been tilted to. So this one is tilted in a way that it can reflect only say a blue light. And this is tilted in a way that it can reflect only say a green light. This is tilted in a way that it can reflect only say a red light. Is that okay? So they are all tilted in a particular way. Is that okay? So that tilting and the angle is what we call the Bliss angle. And that is the small angle that we have here. Is that okay? And that wavelength that is needed to be diffracted on that tilt angle is what we call the Bliss wavelength. Is that okay? So these two parameters is very important. The Bliss angle and the Bliss wavelength. Is that okay? And of course, it's very, very dependent on the diffraction efficiency. So this one still talks about what he spoke about. And some time ago, when we were doing interference, I mentioned something about monochromatic. Do you remember anything like monochromatic? When you say some monochromatic, what does it mean?
So it means that it's single wavelength or one wavelength.
Perfect. One wavelength. In fact, through diffraction grating, you can build a device that we call a monochromator. Is that okay? And now a monochromator is just an optical device that is used to what? Isolate a single wavelength from a mixture of what? Wavelengths. And it's through this diffraction grating. So you can see one grating that is sitting down here. This type of grating is a reflectance one. So the light is going to hit on the surface and it reflects. And when it reflects, it separates all the wavelength of light from the white light. Now we have a slit here that can move. So if we want to separate only the blue, we move the slit to the blue one, then we separate. If we want to separate only the green, as we have here, we do that. If we want to separate only the red, then it will separate only the red. Exactly. That is the engineering of monochromator. Now, under monochromation, supposing we have two wavelengths that we want to distinguish. Is that okay? There's a particular way of distinguishing them. And it's very dependent on something called a resolution. And you know, even when you are buying a TV or TV production unit, they are coming. Today, Samsung will say they have a TV and the resolution is, say, 720 pixels. Another one will come and will say it's 1080 pixels. Another one will came is 4K pixels, you know. So there's a resolution that is coming. And resolution is how detailed we can define two different parameters. Is that okay? So if you have a TV, like the Etikopor that we used to use, if it's even two colors, it can't differentiate between two colors. In fact, even before that, it was even black and white. So if it's red, it's green, it was representing it as a what? As something we call a grayscale. Is that okay? So it couldn't differentiate between two colors. Now with time, it was able to differentiate two colors, but not in a very resolved manner. And another time came, now we are able to resolve it through LEDs. Another time came, even with the LEDs, we can what? Build more pixels in it to define a good resolution of the screen. And that is how Samsung and even iPhone, they are eating our money. This year like this, they are releasing, I think next month or next 2 months, they are releasing iPhone 17. And I've seen that they are talking about another K of resolution, how their camera can resolve two different distinct, either spatial or spectral parameters. Exactly. So resolution is a general perspective. We want to see how possible we can distinguish between two wavelengths in our situation here. So here like this, if you are talking about resolution, we want to see how best we can distinguish between, say, this color and say the blue color that we just removed. Is that okay? If we are able to distinguish between the two of them very well, we can say the resolution is good or the resolution is bad. Is that okay? So any device that can do that, that is what you use to define the resolution of the device. Is that okay? Now, in the criteria selection and resolution, there's a procedure that we call the relay criteria. Exactly. And of course, that one too came in the way of giving us a boundary how to select or define two wavelengths of a peak or resolve two wavelengths of a peak. Exactly. And here I define the resolved as what? Distinguishing it between two others. And this is what Relay said. Relay is saying that if we want to resolve two wavelengths, exactly, then what we have to do is that the two wavelengths are resolved if the central maximum of one diffraction pattern falls on the minima of the other one. Is that okay? And in simple terms, it's presented here. In simple terms, we are saying that the central peak should what? Should touch each other. Is that okay? So you can see one wavelength has a peak here, and another wavelength, let me use a reference to pass through. One wavelength has a peak here, and another wavelength has another peak here. Exactly. So relay is just telling us that if we have a situation like this, we should be expecting that the half minimum is okay, should be touching each other like this. And that is the criteria of relay, separating or defining what resolution of two wavelengths. Is that okay? In fact, there is another way in actual sense of our way of resolving two wavelengths. We could have one wavelength, say the peak here, and another one, the peak here. And we can see that, oh, we've separated it very nicely. Is that okay? But this is just relays decision or criteria in selecting two wavelengths. Is that okay? And we just have to know that this wavelength should have its half here that is being touched to each other. Exactly. But it doesn't mean that they should overlap. We don't want an overlapping situation like this. Exactly. This is not relays procedure. Relays, we have one peak here and we have another peak here. And only their middle part here is touching each other. Okay. So you can give me a thumbs up if I can go on. Okay. Now, mathematically, we can also define this. And we are familiar with this formula a little. Without this value here, without the 1.22, we are familiar with sine theta equals the wavelength divided by the d. Is that okay? We bring in the half here because we have something we call the area disk, which I'll be explaining later. So let's just hold on to that. Is that okay? By the end, if we have one object of a wavelength, we have another object of a wavelength. Relay is just telling us how we can resolve this to, is that okay? Where we should be expecting that the two half here at the middle should just touch each other. Is that okay? And we can use this formula to actually find for the angle that we need to do that, the wavelength, and even the distance of the aperture that we have to use. Is that okay? Now, let me explain what we call the area disk here. Supposing there's no diffraction in any optical system, supposing, you should be expecting that when light passes through here, you should be getting a very sharp edges like this. Very, very sharp edges. But that is not the situation. Whatever be the case, you are going to get something like a diffraction. Is that okay? Because anytime light enters a hole, it doesn't just go straight, it spreads out, as I said earlier. Is that okay? And that is what gives us this blurry situation like this. And this blurry situation, we can define it as what you call the diffraction blur or iridics. Is that okay? So anytime you use an optical component, you should be expecting something like this. Is that okay? You should be expecting this ring manner of things coming to form on your screen or anywhere that you want the light to go. You will never see a very sharp situation like this. Now, there's something that we call the diffraction limit. And the diffraction limit is just representing the smallest angle of resolution. Is that okay? And you see, if you have a very small angle of resolution, it means you have the most powerful resolution. Is that okay? Ideally, it's not possible to get the very maximum one. Is that okay? So we have something we call the diffraction limit. The very possible way that we can get the smallest angle of resolution. And that one was defined by Lord George. Is that okay? And he was just talking about the fact that supposing we don't have any optical system, in essence of any optical system, it means that it has to reach a theoretical limit of resolution due to what? Diffraction. Is that okay? But in a real sense, in an ideal situation, this shouldn't happen. Is that okay? This is what it has to happen. Is that okay? So light enters a small aperture. You shouldn't be expecting the light to go straight. You should be expecting the light what? To spread out. Is that okay? And you should be expecting a what? An airy or a fuzzy shadow like this. So this is just an add up for the one that I just explained earlier. And in fact, this, I don't know if the model was talking about this, but I just brought in this for our understanding, where we can relate the diffraction limit and something we call the numerical aperture. Is that okay? And when you're talking about numerical aperture, you're talking about the width of the slit and the focal length of the lens. Is that okay? So supposing we have a light source here. Is that okay? And here, this is our small opening. That is our lens here. And the lens here is very dependent on the numerical aperture. Is that okay? And anytime light passes through the lens, you will still get this airy disk situation. Is that okay? Now, this airy disk situation can, of course, we can see the colored one that you see here is the bright fringes. The white one that you see here is the dark fringes. The colored one is the bright. So the deep one at the middle here forms the very peak that we have here. Is that okay? Down the small one here, that is the minima. That is the white one. Then another one comes here as the peak, small peak here. That is the middle one. The another one comes here as the minima. That is the white one here. Is that okay? So we just get this constructive and destructive interference situation anytime we use an optical component like even a lens. Is that okay? Which is very normal. Exactly. And again, there is no way to go out of what a situation like this. It's a limitation in optical components. Now, there's a formula that actually relates these two. That is the spacing, the D. Is that okay? The numerical aperture, and of course, the wavelength. And we have 2.44 here because of the two factors here. If you have 1.22 here, we have 1.22 here. The two of them, since we are measuring the two ends here, we are just going to add the two of them and we get 2.44. Is that okay? And that is how we can relate the numerical aperture, the wavelength, and what, and of course the actual aperture of the what of the lens. So I've done a little add up here for our understanding. Is that okay? So what I've added here is telling us the size and how the numerical aperture affects resolution. Is that okay? So if the numerical aperture is high, what happens to the resolution? If the size is high, what happens to the resolution? If the central spot of the source is say high, what happens to the resolution? And even if there's an overlap, what happened to the resolution? Is that okay? So I just added this one for our reading and our understanding purpose. Is that okay? Now let's try and bring these two scientists on board. We have one called the Fraunhofer and we have one called the Fresnel. And they all did a very wonderful work in diffraction. And they were all defining or explaining diffraction phenomena in two different perspectives. So Fresnel came and he said that if we have a light source, you see, when you are talking about diffraction, we are talking about a light source here, a slit here, and a screen. Is that okay? So light enters and light spreads out. Now, when Fraunhofer came, he said that anytime we are dealing with a situation like this, and we have our light source and our screen at a very far distance, in fact, infinite distances, from the aperture, we call it a far field diffraction. Is that okay? And Fresnel also came than explain the fact that if we have another situation like a diffraction happening, but this time around, the light source here is at a finite position. Is okay, that is at a small distance. That is where we have something we call the near field diffraction. So here is a far field diffraction, here is a near field diffraction. The far field diffraction, the light source and the aperture is at a very long distance, infinite. Is okay. But when you're talking about the near field, the two of them are in a finite distance from the aperture. And this is our aperture, the slit here. Is that okay? In fact, when you're talking about Fraunhofer and first law, Fraunhofer is mostly used mathematically because of the ideas and how we can actually use it here. In fact, when light is from a particular distance and it enters into an aperture, it doesn't behave like spreading out. It behaves like going straight. Is that okay? So it makes it more easier when using Fraunhofer as compared to the Fresnel, because the Fresnel is very, very complicated if we want to actually experiment it in real life. Exactly. And even in the mathematical ways. So let's look at how the Fraunhofer behaves. So you see, as the light is coming from an infinite distance, if it enters an aperture, ideally we expect it to behave like this. But because light is traveling at a very long distance, when it enters an aperture, it doesn't behave like that. It goes straight as it's coming. Is that okay? And if we have a lens there, we can actually easily focus it on the screen. And that is why it is very, very, very easy for us to observe a satellite and other terrestrial objects at the space with a telescope here. Is that okay? So we have our lens, then we observe it on the screen, then we can see what is actually going on easily. So you can imagine a telescope from this point of view, like your screen, your eye watching it from here. Is that okay? If your eye is watching it from here, you can see that if the lens is here, there's another lens here, you can actually observe anything that is from a long distance. Is that okay? Because if light is traveling from an infinite distance and it enters an aperture, this time around, instead of having it spread out, the light actually goes through it straight as it's coming. Is that okay? And it can easily be focused on the screen. This in real life is very difficult because it will be very difficult for you to observe a diffraction on a bench. Is that okay? But mathematically, we use it a lot. And if we are talking about Fresnel, because the distance between the light source and the screen is at a very short distance, it's easy for us to do this on a bench. But how to observe what is going on here becomes more difficult. Is that okay? Because there's a spread out of light after it has exited from the aperture. And I think I wrote something here that anytime you are dealing with something like this, you should know that the distance between the light source to the aperture and from the aperture to the screen is much greater than the aperture of the size. Is that okay? Divided by the wavelength. So the distance here, so this is our light source. So the distance from here to the aperture is okay. And from the aperture to, of course, our screen here, the distance should be much, 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 much greater than the what? The aperture size here divided by the wavelength. The same way as the first law. But this time around, we expect that the distance from this end here and this end here, the light source and the aperture, and of course, the screen and the aperture should be much smaller compared to that of the size of the aperture divided by the wavelength. Is that okay? So that is the only difference. So one is opposite to the other. Is that okay? We expect that the distance between the two of them to be much greater. Yeah, we expect the distance between the two of them should be much closer. Exactly. So I adapted this one from the model where they are trying to compare the Fraunhofer diffraction and the Fresnel diffraction using some different common parameters like the waveforms, the observer distance, the moment of the diffraction, the surface calculation, and the diffraction pattern. I have some questions here. I have some questions here. And we move to Unit 6. Any question for me before I continue? Or I'm confusing you? Is it a little bit better? Okay. Does it mean I can go on? Okay. So the last unit, we'll be talking about polarization. One common application of optics. So now a lot of people are wearing lenses, and some lenses, if you are in a room, is clear. If you enter the sun, then you see that your lens will turn dark like a sheet, and that is a very nice application. And as of now, if you are some fishermen, they do have a particular glasses that they wear, and when they wear, they can actually see very well in the dark. Sorry, in the sun and even in the sea. Is that okay? If the water is very clear enough, we can see what is actually going down there, like the fish is moving and other things. And as of now, too, we have some people that can't drive at night. We have some glare shades that they wear that can help them to drive. Exactly. To prevent, is it when you are driving at night, the headlights that meet you up and other things. Some people headlights, even if it's dim, is more than high, exactly, which affects the eye a lot, and it can easily cause an accident. Through these principles, we have some glare shades that people can wear to prevent all these things. So we'll be looking at polarization. So in the early beginning of our slides, we spoke about electromagnetic radiation. And we said that it's under a transverse wave, and it doesn't necessarily need a medium to travel through. Exactly. So even in a vacuum, electromagnetic radiation can do perfectly well there. And you know, anytime you have electromagnetic radiation, it consists of two radiations particularly. You have that of the the electric, and you have that of the what? The magnetic. Is that okay? That is traveling perpendicular to each other. Now, when you are talking about unpolarized light, even your room there, the light that is looking at you is unpolarized. All the random lights, they are all unpolarized. When you're talking about unpolarized light, you see, these lights are emitted from, say, some atom and other things. Is that okay? But their vibration pattern is very, very important. Is that okay? And this time around, their vibration pattern is into all angular of direction. Is that okay? So if we have a situation like this, and you can think about it like a point of light that is a ray that is going this way, and supposing we observe it from one end here, you can see that our vibration may be going all angle that we don't even expect it to happen. Vibration in all angle, exactly. And a situation like this is what you call an unpolarized but light. And you can think about this one like a tennis ball, where let's say we have should I use a tennis ball? Maybe to get us confused. You let's go on. If and a question comes, then I have to use that. Then I'll bring that scenario. Now, under polarization, we have ways of making an unpolarized light polarized. We have way of selecting all the different direction of the vibration to only one particular vibration. And look at what I have here. You see, we have a light here, and the point here is vibrating at so different angles that we don't even expect. Unregularized manner of vibrating. Is that okay? Now, if we have a polarizer, I will explain a different type of polarizer. But in case we have a polarizer, and this polarizer has the ability to select only one axis for us. Is that okay? So here you can see that it's traveling in so many different axes. Is that okay? So if this polarizer has the ability to select only one axis, like the straight one that we have here, so anytime an unpolarized light enters, it will chop all of the rest off, and it will give us only one axis as this that we have here. Is that okay? Now, if you have a situation like this, we are saying the light is what? It's not polarized. And in fact, there are so many ways of polarizing a light. But the three main categories, the first one is a selective absorption, The second one is the reflection. The next one is scattering. Is that okay? And this one, light will pass through. Is that okay? And it will absorb all the different direction and allow only one to go through. This one to reflection, light will hit on the surface, and unpolarized will hit on the surface, and it will absorb all other one and allow only one particular axis to reflect off. Is that okay? And the scattering too, light will hit the surface. Is that okay? And this time around, it will be it will be polarized at a particular direction depending on the scattering plane. Is that okay? So there are three particular categories when polarizing a light: the selective, the reflection, and the scattering. Is that okay? Now, there is this man that helped us in finding ways or the intensity of the light that is polarized. So supposing this is our light coming here, we can find the intensity. You see the intensity, it has its own intensity, like 10. When it gets polarized, the intensity may reduce. Is that okay? Now, when it's reduced, Muller's law has a way that it can help us find the intensity that we now have as a polarized light. Exactly. Which I'll be talking about later. But the formula here is just the intensity of the final one equals the intensity of the initial one, sine what? Theta. Sorry, sine square theta. And here, the theta here is going to be the angle that we've shifted the polarizer. And maybe during your practical section, when you come, I'll show you some polarizers. We have plenty of them lying. Now let's look at something here. The angles, maybe we can relate the angles here. Now we have A, B, C, D, E, F. The very last one here is an unpolarized light. And now you can see that it's in only say two directions. And we can look at this one from a perspective of sideways, maybe. Is that okay? So we can look at it in sideways. And this one, we can look at it in a front way, where we have it moving horizontal and vertical. And here we can look at it in, say, looking at it in only the vertical perspective. Is that okay? Now, if we polarize it, and the polarizer has an axis, or let's say an opening like this, that allow only the vertical to pass through, it means the horizontal will be chopped off. Is that okay? And in a situation like this, we will get the what? The D. Supposing we have another polarizer, then the polarizer has an axis of only the vertical, and it can allow only the horizontal to pass through, but the vertical will not pass through. Then it means we get our polarized light as this. Is that okay? So depending on how the polarizer angle is, it will influence how we are going to get our polarized light. Is that okay? Whether we're going to get it at, say, horizontal, vertical, or at any angle. Is that okay? But in a situation where we have our polarizer, and let's say the axis is something like this. Sorry. Will we get a polarized light? Are we online?
So we are here.
Okay, so will we get a polarized light? Supposing we have an unpolarized light like F, and let's say our polarizer has an axis like this, a diagonal axis like this. Will we get an unpolarized light? Is it that we don't understand, or
The understanding is not clear.
Madam Fisher, you didn't tell me the understanding is not clear. I asked a question and
Yeah, so we'll say, Oh, dear. Say, please.
okay. Any other person apart from Madam Fisher who can help us here? Yeah, hello, Sir Isaac. Are you trying to? Sir Nephew, do you want to come on board? Sir Nephew. Hello, Sir George. Let me mention names. Yeah, Sir Eric, come on board, I beg.
All right. I think it will be polarized because the light will take the direction of the that hose, so that the other side will be chopped off by the polarizer.
Okay. Okay. So, thank you, Sir Eric. So, for the sake of Madam, Felicia, let me go back a little. So, anytime we are saying that anytime light is traveling, the particle vibrates at different directions. Is that okay? And it's not only X and Y direction, like different, a lot of angles. Is that okay? A point like this travels in so many directions. So you can imagine points like this, another one in front, a lot of them in front. And that is what we call an unpolarized light. But we have ways of polarizing the light so that we just tell the light to travel in only one axis. Is that say, okay? So we can tell it to either travel in, say, angles at diagonal, vertical, horizontal, anyway. Is that okay? And a device that can help us do that is what you call an analyzer or a polarizer. And depending on the axis that the analyzer or the polarizer comes with, that is what is going to be polarized for. So you can see that this one, our transmission axis is straight. You see, it means it will remove all other angles of movement and allow only the straight one, as in this manner, to pass through. So you can see that from the results here, the light is traveling through. The results here, the one that is polarized is the one that is as straight as this. The rest, nothing goes through. It chops the rest off. And it's the same situation that we have here. So you can see that what we have here, we have an unpolarized light like this. For us to get something like, say, E, it means that we need a polarizer that can behave something like this, where the axis is only on the vertical. So when a polarizer, an unpolarized light like this passes through, we should expect all the rest should be chopped off and only the one at the vertical to pass through. The same way, if I have a polarizer like this, and I have an unpolarized light from all these angles traveling through, there's no way the horizontal like this will pass through. Only the vertical, as in how this axis is arranged, that is what is going to pass through. And it's like you have a fence. You see, first they do this wooden fence straight there, and you remove only one end here. Exactly. And this time around, you are trying to push something that is horizontal through that vertical. It's not going to be possible. Exactly. If it will go through, unless it is as vertical as the fence before it will go through. Exactly. And the question is, I have an unpolarized light as the vertical and the horizontal. But this time around, my polarizer is a diagonal polarizer on the axis, on a particular angle. Let's not define the angle, but it's diagonal. And I'm asking, in a situation like this, will I get a polarized light?
No, sir.
Or we are still not getting it?
Sir, for the C.
Yes.
So
So
Mika is
for
talking about the C.
so the
C.
C and the F is the same, but
Yes.
we are looking at it at different angles. This is the front. This is the side view. Is that okay?
Okay.
So
Okay.
let's just imagine the front as the F,
Okay.
and we want to check if the F here can pass through this polarizer, because I've explained that if F here goes through this polarizer, the one just down it, we are going to get an answer like the D. Is that okay?
Okay.
Because
Okay.
it will remove the horizontal and it will let only the vertical pass through this.
Okay.
Now, if the F passes through a polarizer like what I have here, it will remove the vertical and let only the horizontal pass through. And that is what I'll get as the E. Is
ES.
that
Okay. Exactly.
now I want to know if I have a polarizer like this, what will be my results?
So this is diagonal.
Mm, Therefore, do you want to come on board?
I want to try.
Try.
Then when you look at the C and the F, you said they are the same, right?
You are talking about
Yeah.
the F is diagonal.
But you said the C and the F are the same. Oh,
Yeah, the C and the F are the same. So the C, we are
okay.
looking at it on sideways, and the F is the front. So here, the F, we have a lot of them following up.
So for me, I think because of the nature of the F, it is like horizontal and vertical, right?
Mm-hmm.
So if it is passing through a polarizer that is vertical, definitely if you chop off the other side, then it will pass through vertically. And if it's horizontally, if you chop off the other side, it pass through horizontally. But with this one that you're talking about, it's diagonally.
Mm-hmm.
And when you look at the nature of the F, it cannot polarize it. That's what I think. Because
Perfect.
it's horizontal and vertical. Mhm.
So it's perfect. So it will not polarize it. So to chop off both the vertical and the horizontal of this polarizer, and nothing will pass through at all.
Yeah, nothing pass through that.
So it's good. I like the answer. So
And so
please,
in short terms, the polarizing will only take place both in vertical and in the horizontal, not the other way around. Let's say
polarizer can pass
diagonal.
through in any angle. It depends on the unpolarized light entering. So
Okay.
supposing we had a polarizer like this, pen, that is traveling in this manner,
Mm-hmm.
and this manner, and
Mm-hmm.
this manner, and
Mm-hmm.
this manner, let's say a lot of different angles, and it
Okay.
passed through a polarizer like this, you will still get some light coming out,
Okay.
because we may get some of the angle that may be the same as the axis here. Because when
Okay.
you look at the axis that we have here, it's the same axis that we have here. So it means that to chop off every end and allow only this axis to pass
Two.
through.
That's true.
Is that
Okay.
okay?
Okay.
But a situation like the F is only the horizontal and the vertical.
Okay.
So horizontal will not pass through, vertical too will not pass through, and that will go. Is that
All
okay?
right.
But what we
Okay.
have to put in mind is all unpolarized light travels in different angle, like something like this. Like a lot of them travels in different angle. Is that okay? Different angles. Is that okay? So when you get an unpolarized light, depending on how you tilt it, you may get some of them passing through.
Okay. Thank you, sir.
Okay. So now let's look at something we call dichroism. In fact, is a material that exhibits something we call the selective absorption, which I've explained to you. Is that okay? I told you that we have the selective, we have the absorption, we have the reflectance, and we have the scattering and the polarization. And this one behaves in a situation where the light will pass through, absorb some of them, and allow the rest to go through, depending on the axis of polarization. Is that okay? Now, if we have a situation like this, we should be expecting direction to actually place a factor a lot here. And a very typical example of dichroic material is what we call the tourmaline. So it's a very typical example of what a dichroic crystal is. The most important thing that is here for me, for you to understand is these two scenarios. So you see, we have a light source here. We have another light source here. Let's talk about the P. If the first polarizer, we have two polarizers here, 1 and 2 here. If the first polarizer has an axis that is vertical, as you can see here, and light passes through, this unpolarized light passes through, we should get only this axis pass through. Is that okay? But my question is, if we have a second analyzer here or polarizer here, will the light here go through? Will it go through? Hello.
Sir, please, the line is breaking now.
Okay, so I'm asking the class that, hello, is it clear? That I have two polarizers. So the first one is here, the second one is here. Is that okay? And I have an unpolarized light here. That is going to go through this polarizer. Now, if it goes through the first one, because my axis of polarization for the first polarizer is on the vertical, I'm expecting that my polarized light should also be on the vertical like this. Is that okay? Now, my question is, if I have a second polarizer as the first one as this, will this light pass through it? Yes, and yes, fire.
I think it will pass through because the hand is vertical.
Very good. It will pass through. But let's look at the A. You see, this time around, the polarizer or the analyzer is turned to the horizontal. Will it pass through to the detector?
No, sir. It can't.
No, it will not pass.
It will not pass through. Simple. Is that okay? So what I'm trying to say here is the axis of the polarizer do matters a lot. Is that okay? Now, there's something here that we have to look at. Okay, I think this is an answer for a question. So let's hold on to this. I'll come to it later. There's something here that we have to look at, and here is what we call the Malus law, which is very important. I showed you briefly how Malus law behaves, but this is a very typical example again. And let me just use this one to explain. So if we have an unpolarized light here, and we have a polarizer like this, and you see the axis of the polarizer is on the vertical, so it will allow only the vertical polarized light to pass through. But interestingly, we have a second analyzer, and the axis is tuned at an angle a little. Exactly. It's not completely like an horizontal. It's just tuned a little. In fact, from Malus, it means that the lights will not go through, but you have some small intensity reaching behind here. Exactly. And we can use a formula to calculate the intensity that we get here. Exactly. So what he's just trying to say is, if I want to write, if I have the intensity of light here as say 10, and we have some polarizers here, depending on the angle that we've moved the polarizer, we can calculate the intensity of light that reaches the final destination here. Is that okay? And here, the formula is very simple. It's just I, that is our final intensity that we are looking for, equals I naught. That is the initial intensity or the incident on polarized light, cos squared theta. Is that okay? And the theta here is the angle that we've moved the polarizer. Is that okay? So if we move the polarizer at 20 degrees, we have to bring it here. If you move the polarizer at 30 degrees, you have to bring it here. If we move it at 90, we have to bring it here. And after that, the I naught here is going to be the intensity of the unpolarized light that is entering. Or if we start calculating here, it will be the intensity of this polarized light. Should I go over or you understand?
Please go over.
Okay, so what we are saying here is Malus demonstrated how we can find the intensity after a light has passed through a polarizer. Is that okay? And what he was saying here is, The angle that we move the polarizer is very, very important. Is okay. So supposing I have an intensity of light here, I see I naught. And I want to find the intensity of light here as I. Per this formula, I should be able to find the intensity. Is that okay? So if I know the I naught, and I know the angle that I have moved the polarizer, that is theta, I should be able to find for I using this. Is that okay? So I just have to put in the intensity of the I here, bring in the angle that I've moved the polarizer here, and I can find the I here. Is that okay? Supposing there's another polarizer here, and say that one to have moved it per a particular angle, I have to relate the intensity I have here and the final intensity that I have here. But maybe that one, I'll talk about it later so that I don't confuse you. But do we understand this so far? Now this is our I naught. This is our I. If I want to do the calculation, in fact, this calculation is for this polarizer or analyzer. If I want to do the calculation for this polarizer and analyzer, this is going to be my I naught. And here is going to be my I. Is that okay? So depending on which polarizer that you are using, the one that comes before is the I naught, and the one that we get after the polarizer is the I. Is that okay? So we can find the final velocity, sorry, the final intensity of the what? Of the polarizer. Are we
It's
okay now?
from which direction?
So please write the
Okay,
Which
so the
direction is the
direction,
light
the
moving?
direction
Or it
is
didn't
going
indicate the
this way. So the polarizer passes through up to this end, and it passes through up to this end. Is that okay? So here, this is my first I naught. It passes through, I get my I for this polarizer. Now there's a second polarizer. If I've tilted, this is going to be my I naught. It passes through, I get my I. Is that, supposing there's another polarizer, this is going to be another I pass it through, I get my I. Is that okay? So it's for the individual polarizer correlation that you are doing.
Oh, so I wanted to ask the formula that I not cos square theta. The reason why it is the cos is squared, or it's because it's a constant formula.
Oh, okay. I was trying to skip that, but we can go through that. In fact, when we find the angle, we're supposed to get E naught, and here the E naught is the amplitude. So we're supposed to get E naught because in fact, sorry, it's not E naught, it's E equals E naught cos theta. Sorry about my handwriting. When you relate these angles that we have here, so supposing this is our angle here, this is our I naught, that is the amplitude. We're supposed to get the I naught. Since we are interested in the new one here, we're supposed to get E naught cos theta. But amplitude and intensity is related, and we call it instantaneous amplitude, and it's related as the square of the amplitude. That is what we have here. Exactly. So if I want to find the intensity that I am interested in, it means that I have to square this. Is that okay? And in the process of squaring this, I have to square this whole thing here. Is that okay? And at the end, I will get my E naught squared cos theta, cos squared theta. Is that okay? My handwriting. And if I do this E naught squared is the same as I. Is that okay? So I can ignore this and just write I naught. Is that okay? That is how we manage to get the I naught cos squared theta.
Okay, sir.
Yes, sir. If your hands is up.
So please, you showed, sorry, you showed a particular page or a slide where my line was, it was not clear, so I couldn't really hear what was going on. But then I want to ask a question. I think it was in two dimensions, the unpolarized light,
Mm-hmm.
like vertical and horizontal. And please, I want to ask, can we, is it like for physical property or feature of unpolarized light, can we have it in that manner? Is it like they span, always span in all directions, or we can have them in vertical and horizontal orientation?
Okay, that's a nice question. That one that I shown was just a demonstration and illustration. In a
Oh,
typical sense, an unpolarized light comes in so many angle of direction. Is that
oh,
okay?
all right.
Unless maybe I have a polarizer where the polarizer can fuse out only the vertical for me, and I have the others as say the vertical and the horizontal. That is where I'll get something like this. Is that
Oh,
okay?
okay, so
But
that one was just for an
explanation.
analogy for the question, for a question.
Yes, yes. Is that
Okay,
okay?
all right. Thank you, sir.
In fact, even the unpolarized light that we see here, the angles are more than the directions that is showing here. Like
Yes,
it comes in so many directions,
yes.
indefinite ones.
Right. Okay, thank you, sir.
Okay. Now let's look at something. So this is for the Malus law demonstration. Exactly. So let's keep this formula in mind. You'll be using it. And I think there's a question that I was trying to solve here that use the same demonstration to solve. So the question is there, and this is the answer. So when you finish solving, you can look at it then check if you are doing the right thing. So we can actually do polarization in reflection mode, as I explained earlier. In fact, when light actually hit on the surface, the surface of a water, surface like a prism, is that okay? We know for sure that some of the light, most of the light enters the sample, or say our prism, or say the water, and it gets diffracted. Is that okay? Either bending towards the normal or bending away the normal. And we have a partial reflection that is going to go on. And that is going to be our angle theta here. Is that okay? So there's something that happens that correlates with polarization here. If we have our reflected beam and the refracted beam relating as a 90 degrees, that is where a polarization happens. Is that I'm repeating. I think someone phone is on, so it's interfering. Okay, so I'm repeating. So when light hits on a surface, an unpolarized light, is that okay? So we have an unpolarized light coming to hit on the surface. Now, when it hits on the surface, we know for sure that a lot of things do happen. And a very common one that we've all gone through one way or the other is what we call the refraction. Is that okay? So most of the light will get refracted. And we may get some partial reflection. Is that okay? Where some of the light will just go up. Is that okay? Then what we have to know that the angle of incidence is the same as the angle of reflection. Exactly. But it's not the same as the angle of refraction because it depends on the density of the medium or how well the medium is for this one to move close to the normal or move away from the normal. But the most important thing is I'll forget about the what is here. Let me show you. Look at the diagram here. The most important thing is here. Anytime we have our reflected beam 90 to the refracted beam, this beam here becomes what? Polarized. Is that okay? I'm repeating. So we have a light coming. It hits on the surface. Some goes down here. Some comes up here. But anytime the angle between what goes up and what is down here is 90, this light here becomes what? A polarized light. Exactly. And here we call it what? A Brewster angle. This angle here, we call it what? A Brewster angle for polarization to happen. Is that okay? And in fact, there's a simple equation as this that can help us find for a Brewster angle. If we know the refraction index and we know the say we want to find the angle, we can easily find the angle if we know the refractive index. Yes, Sir George.
So please, my network, I went off and I just got here. But please, which of from the diagram, which of them is the polarized light? Is it the reflected or the refracted ray?
The reflected. The
Okay, that's the
the
polarized.
yeah, that's becomes the polarized light. And you see,
Okay,
this one dates. Okay, you're welcome. This one dates back from Snell's law. We know that from Snell's law, when Ni, that is the one from A, and the sign of the P, that is the angle here, is going to be equal to the N2, that is the refractive index of what is inside here, and the sign of the angle of refraction. And in fact, because we're expecting that anytime we add these two angles, we should be getting 90. That is, anytime we add this angle, and of course this angle, we should be getting 90. Anytime we add, let's write the theta p plus the refracted angle, we should be getting 90. Is that okay? And it makes sense because this is to 180. And if these two angles that is happening is 90, it means that our sine 2 here and plus our sine p here, sorry, our angle p here and our angle 2 here supposed to be what? 90. Is that okay? Now, because this is 90, if I want to make, say, the sine 2, sorry, the angle 2, the subject, that is going to be 90 minus our angle P. Is that okay? The theta P. So this is what I have inserted here. Is that okay? So now I've removed the theta 2 and I've replaced it with this angle. Is that okay? Which in trig, when you open this up, you are going to get what? N2 cos P. Is that okay? So the angle P, sorry. Now, if we have a situation like this, now this is being ignored, and from trig we have gotten this, and we want to make, say, we want to bring in a tan inside, exactly, so that we ignore the cos and the theta, because at the end of the day, they all have the same angle, exactly, as in our theta p, our theta p. Then we can have n2 over n1, and now we know that our n1 here is from air to, say, the medium, say glass or water. Our n1 here ideally is 1. So we can just ignore this one with the other. Then we know that our sine theta p cos theta p is the same as tan theta p. So it means at the end of the day, we should be getting something like our n2 here to be equals to the tan theta what p. Exactly. Where the angle here, that's the theta p, is called the Brewster angle. And the n2 here is the refractive index of that medium, whether being air or anything. Exactly. So if I have a situation like a liquid or say any prism, and I know the refractive index, I can calculate for the Brewster angle so that I'll position that particular, the Brewster angle is almost the same as the incident angle. Position a beam of light on that particular sample and get a polarized light, which is very phenomenal one with the other. Is that okay? So if I have, say, a refractive index of, say, 1.33, and I calculate for n, sorry, I calculate for theta p, which is going to be the sine inverse of this whole thing. Is that okay? So the theta p here, the angle that I'll get is telling me that anytime I place an incident light on that particular angle, I should be getting what? A polarized light. And that is the Brewster angle. Please, do we understand? You can give me a thumbs up if you are good. Great.
That is good value.
Yeah, I didn't hear what you said.
I think it's good value. The value.
Hello.
I'm saying that I said I should go over there, Costa and go over there.
I should go over again.
You said you
Yeah,
should go over the booster angle again.
The booster angle. Okay, so it starts from here. When we have unpolarized light coming here, some of the lights get refracted, some of the lights reflect. If you are traveling from one medium to another medium, and in fact, when travel from a less dense medium to a more dense medium, like say water to air, water to prism, or any manner, is that okay? Now, what we are saying is that for us to get a booster angle, it means that the angle between the reflected beam and the refracted beam should be 90. Is that okay? The reflected beam and the refracted beam should be 90. Now forget about the incident beam. Now if the refracted beam and the incident beam, they are 90, it means that my angle here and my angle here can also be equated to what? To 90. Is that okay? It means that anytime I have, you see, on a straight line, we expect the whole angle to be 180. And we have some parts here that is taken off as 90. So it means this here and this angle can be equated to 90. So it means I can write, say, my theta p plus my theta 2 to be equal to what? 90, which makes sense. Is that okay? And from Snell's law, we know that Snell's law is always as written as this, where we have the refractive index of the first medium and the angle of that first medium, refractive index of the second medium, and the angle of the second medium. Is okay. So here, theta p is the incident angle. Here is our refracted angle. And from what booster angle is telling us, or Booster's law is telling us, it means that if I have theta 2 here, I want to ignore the theta 2 and just represent it by the theta p. Is that okay? So I can just make theta 2 the subject here, and at the end of the day, just get what? 90 minus theta p. Is that okay? Then if I do it that way, it means this is off. It's represented as this because of this equation. Is that okay? Now from trig, if we have sine theta or sine of two parameters here, it means a sine of the first parameter, cos of this parameter, minus cos of this parameter, sine of this parameter. And in fact, when you do that, this is what you are going to get. Is that okay? This term here is going to be ignored and it's going to be represented by what? Cos theta p. Is that okay? Now, we know that anytime we have a sine and a cos of the same angle is the same as what? The tan of the same angle. Is that okay? So if we make n2 over n1 the subject, we are going to get sine theta p over cos theta p, which is the same as tan theta p. And here, because we are traveling from air to a medium that is dense, the effective index of air here becomes 1. So we can ignore the n1. Is that okay? And of course, if that's the case, we are just going to get straight away n2 to be equals what? Tan theta p. In some books, you may not see the angle as theta p. It can be phi, it can be theta, it can be any angle they put it there. But at the end of the day, you have to know that if we are finding booster angle, is the tan of the angle equals what? The refractive index of that particular medium. You may not see n2, you may see only n, that is fine. But we are just interested in the refractive index of that particular medium. Say, are you okay?
Yes, sir. Thank you.
I think another hand is up. Say, Anefi.
All right, sir. So please, I want to have some clarity here concerning the brief test angle, which is the theta p. Is it like it is achieved or it is gotten when or at a point where the reflected ray and the refracted ray are perpendicularly arranged, to each other? As in, if both of them are perpendicular to each other.
Yes. So you cannot arrange that Is that okay? Is the
No,
law that derived it for us in that perspective? Is that okay? But
no.
before we get,
Okay.
okay, finish. Sorry.
Actually, I'm not talking about, let's say, me, but then let's say the light is coming from a certain source. So at least it means that you can manipulate the orientation of the light.
Of course.
So what I want to know is that at a certain point where the reflected ray and the refracted ray, which is inside the medium, are perpendicular to each other. Is that the point? I'm asking because of the condition, which is theta 1 plus theta p being equal to 90 degrees. And so I want to know, is it like the orientation should be such that we get a situation where the reflected ray and the refracted ray are perpendicular to each other, so that the K1 and Q2, should be or must be equal to 90 degrees, which is the Brewster angle, which is the theta p.
Yes. So it is the laws. Are you done? Can I answer?
Yes, please.
So
Question
is
is
the laws condition before booster angle can happen? Is that okay?
yes.
And the law condition is flat. That if we want booster angle, the first thing that has to happen is anytime we incident a light on the surface, we should get a refracted beam and a reflected beam.
Yes.
And the reflected beam and the refracted beam should be 90.
90. Okay. That's the clarity I want.
What follows up of we getting the other theta to be equated to be 90 is a mathematical race of the follow-up.
Absolutely.
Okay.
Yes, I understand that. All right. Thank you very much.
You're welcome. So I think we can go on. So we'll be using this a lot. So let's keep it in mind. Is that okay? I think I have some questions that we use this a lot. Let me add another application. I think about the next two slides, we should be finishing. Another application of a typical booster angle situation usage. And this is in the development of a laser. Is that okay? You see, when laser comes out, automatically it's polarized. And it's because of their configuration that goes in here. I dubbed this one from the model. And I don't know, it looks very confusing, but let's try and see if we can follow up. So we have in a laser medium or a laser component mechanism, we have two mirrors that is facing each other. We have one that is very, very reflective, like 100%. It's not like the normal mirror you use in the house, like very, very reflective. In the lab, the mirrors we are using could be like, you will not get 100%. You can get like 80 something, 90 something, but not 100. But the one in the lazy medium is absolutely 100. If not even 100, 99 point something. And they have another one that is opposite it, that is a partial reflecting mirror. Is that when you say partial reflecting mirror, it can reflect and it can allow some of the light to pass through it. Is that okay? So it's behaving in both ways. Now, inside that particular mirrors, or in between the two mirrors, we have something called a booster window. Is that okay? And it's also a particular, let me say, it's not particularly a lens, but let me say something like a device of a different refractive index inside there. And if we have a laser medium in between, and this is how a laser works. We have something called a laser medium inside, and we have a high energy that excites it. And at the end of the day, eject some of the atoms at the ground state, move to a high state, and this tend to move it so that we get our light. Okay. So here, the laser medium is a gas, and it's a helium neon gas inside in there. Is okay. So it gets excited. Now, during their movement through the booster window, that is where the polarization happens. Is okay. And if we have a light here, it goes and it's calculated in such a way that anytime it's coming back here, we have a partial polarization happening at the first booster window, and another final polarization happening in the second booster window before we get our vertically polarized laser coming out. Is that okay? So now let me add up the mechanism here. So you see that first there's a laser medium that is entering here. And I've explained the fact that in a polarization, one way or the other, we need a situation where we have our angle that is between the reflected one and the reflected one to be 90. Is that okay? And that is very important. So if we have our normal here, this angle here is our booster angle. This angle here is our booster angle. Is that okay? And if we are from this angle, we can calculate this angle here and the one that, of course, emerges out here to be 90. And you know, the one that, say, Anefi asked, between these two angles here, this is going to be the incident, the reflected angle, and this angle here is our refracted angle. So you can see that we have 56 here, we have 34 here. The two of them give us the 90. Is that okay? So automatically, we have some light here that is still polarized, but it is rejected. We don't need it. And this angle, light that is refracted enters another medium from this end to this end here. And that is where we get our polarized light. Is that okay? So first, polarization is happening here. Polarization is happening here. So before the light actually comes out from the medium, it is vertically polarized. Is that okay? So booster angle is being applied here, and we call it booster rainbow. Is that okay? Because of the device that is there, then we get a polarized light. I have some questions here too. So one question here, and we are done. Ask me questions before I end the class.
Yes, you are done.
Yes, sir. Everything.
Are you done?
Therapy.
Yes, sir.
Please, can we get the combined slide for all the things that we have treated so far?
So I'll be sending it ASAP.
Okay.
So let's use the rest of the time that we have to go through the questions that I have provided. Is that okay? We have quite some questions here. And concerning your issue too, hopefully tomorrow I'll talk to Sir Charles, and from his response, if it's possible, we will just schedule like a 30 minutes to talk to him. That one to be perfect. And I think Sir George was saying there's a group that has been created. If he can be added so that the concerns will be channeled to him too, that would be so perfect. Depending on how discussion with him goes, and if he wants to be added through that conversation, they will do that. And yes, Sir George.
Please, that group was for only thermal physics, so that the lecturer can be on board, so that you can hear our grievances. So then, if that's there, then we must create a different group, because that one is for only thermal physics.
That is fine. So you don't worry, let him just talk to him. If he agrees that yes, we should create a group, then we just do a quick one. After the discussion, then we dissolve the group. Exactly. Then I think that would be way easier. So you will definitely hear from me. Maybe I have Madam Felicia's number, so I'll communicate to her. Then if there's a need, then she will pass that information to everyone.
Say the slide, you please. We are on our distance.
I'll send it. I think I've shared one before, so I'll get the little adapt that I've done. I'll just add it to them. Share it to everyone.
Please.
Yes, sir.
The part that you explained the polarization, my network went for over 30 minutes. I wasn't on it. I don't know. Since we have time, can you kindly throw a little light on it? If that's the basic explanation. What is polarization of light?
Yeah, Sir George, the class is recorded here, so you can actually go back and listen anytime. I want to go somewhere. That's what I'm trying to do. Is that okay?
Okay.
So just listen to the pre-recorded videos. So that's at least we don't waste some of our bundles. Yeah, Sir George. No, Fire Minister, your hands was up. Oh.
Oh, sir, it's okay. It's okay. I'm okay. Thank you.
Okay, so please permit me to dissolve the class. If but in case of anything, we can just communicate through WhatsApp. Is that okay?
But sir, that's nice. You can electro adapt to me.
I'll add it.
We are not going to change it, so we want to explain it.
Hello,
I'll add
sir.
it. Yes, nephew.
Sorry, please. The question on the screen. Please, do you have the answer? So you could just pass them so we can compare to what we get.
Okay, this one, I think I didn't add the answer for this one, but it's not a problem. I can just add the answer if it's good. Sincerely, I wanted you to just try it yourself, discuss it among yourself. I was thinking that would be way easier for some of us understanding these things. That's why I didn't add
But I'm sure there may be varying answers depending on how people approach it. So at least if you are guided by, a final answer.
Okay, don't worry. So you let me just put this one on the page. Is that okay? Maybe with time, I'll just solve once and add it up. Is that okay?
That's fine, sir.
Okay, so let's all have a nice. We'll hear from ourselves one with the other. Is that okay? Okay, bye bye.
Mr. George.
Master Yapon, kope baby now, koda.
More than a unit, Erasmus, this is Korea man. More than a creative platform behind lecture and Kassan and Pachu.
But you're more than any.
Modern physics, you know.
Oh.
Some was a term idea, yeah, creative platform. And I was one lecture and Kassan, now a big creative platform. Now modern physics, Nana, easy to go and play modern physics.
Yeah, some more. We would only have
the same coordinator for both courses.
And the Erasmus, a coordinator now or coordinating term office, no one a far more than
I know.
okay.